This is part 4 of the series Circumference and Area, and in this section we're going to start out with a discussion of regular polygons. Now, a regular polygon is a polygon that is both equiangular and equilateral. Remember that equiangular means all the interior angles are congruent, therefore they're equal in measure, and equilateral means all the sides are equal in length, therefore congruent. So it's equiangular and equilateral. Here is an example of a regular polygon. This happens to be a regular hexagon, and in this case we have several different pieces of information. First, we have the center. The center is a point that is equidistant from all vertices of the polygon. It's similar to the center of a circle, and in fact, it's the center of a regular polygon is the center of a circle that's been circumscribed around the polygon. And that makes the distance from the center to each one of the vertices of the polygon a radius of the polygon. So a radius is a segment from the center to a vertex of the polygon. So regular polygons have centers and they have radii. And the third piece of information that's really important is called the apothem. And this apothem is an altitude of a triangle made by two radii and one of the sides of the polygon. Now you'll notice that there's one of these triangles for every side in the regular polygon. And since each one of these two sides is a radius, each one of these triangles is at least an isosceles triangle. In this case, they happen to be equilateral triangles in a regular hexagon, but in most other cases, in all other cases, they are isosceles triangles. So that's going to be an important factor that we're going to take a look at. But the apothem is an altitude, and the definition of an apothem is a segment from the center perpendicular to a side of the polygon. So the segment from the center perpendicular to a side. Each one of these triangles has an apothem. And so any regular polygon has one apothem per side. That's going to be another important factor that we're going to look at when we're dealing with area. If we wanted to find the area of this regular polygon, one of the ways we could go about it would be to take the fact that these triangles are all going to be congruent triangles and find the area of one of these triangles and multiply it by the number of sides. And that would get us the area of this regular polygon. Now, in most circumstances, we don't have to go through that hassle, but it's really not a hassle. If you wish to do that, it's perfectly adequate. And in fact, using that approach, that's one method for deriving the formula for area of a regular polygon. So let's go ahead and do that really quick here and show you where the area formula comes from. If we call this side here, let's call this a base, and let's call this the height. It's actually the apothem, but right now we're going to call it the height. So base times height divided by 2 is the area of that triangle. So the area of my regular polygon then is going to be area equals 1/2 base times height, and that whole thing times the number of sides. So let's call the number of sides n. Alright, now, if we take a look inside here, we have the base, this base length, times the number of sides. Well, in a regular polygon, we know that each one of these sides has the same length. So this base length, this side length, times the number of sides is simply the perimeter. So we can pull that b times h out and call that perimeter. So that area is now perimeter times 1/2 the height. Now, if we take a look at what this height is, this height is actually the apothem, the length of the apothem. And so we're going to change that height to apothem. And that gives us, this value is actually the apothem, and that gives us the overall formula for the area of a regular polygon. So the area of a regular polygon is 1/2 perimeter times apothem. So the area of a regular polygon is 1/2 the perimeter multiplied by the apothem. Now one way to think of this, it's a little easier to remember, is if you look at it and say this is 1/2 pi. And so however you want to remember it, whether you want to just find the areas of these triangles multiplied by the number of triangles or use the actual formula. In most cases the formula is going to be easier, but it's entirely up to you, your choice. Now the actual calculation of area of a regular polygon can be a rather rigorous process, so we're going to work several examples and take a look at one of the best ways of doing this, or multiple ways of doing this, and you can pick what you think is the best way to do it. So for our first example, we're going to start out with a basic one just to get a feel for the idea. Now, one of the things you need to think about is you don't need to draw the entire polygon. It doesn't really matter how many sides the polygon has. What you're going to be working with is that one base triangle at the bottom. So it's not necessary to go through all the detail of trying to draw a regular hexagon. You can do that, but it's really not necessary. The only thing we care about is this triangle in here. From the center, this piece right here. That's really all we care about, is that one triangle. Because everything we need can be gleaned from that one triangle. So it's really not necessary to draw the whole polygon. You can just get rid of that and draw this bottom triangle. So let's go ahead and do that. I'm just going to draw a bigger version of that bottom triangle just so that I can put in what I need. Now the next thing I'm going to do is I'm going to draw in my apothem. And these pictures don't have to be perfect, but just draw a representative shape for your triangle. Now we're going to put in the information that we're given in the problem. We want to find the area of the regular hexagon with a side length of 6, so the side length is 6, and an apothem of 5. Well, in this case, they've given us everything we needed, so there's really nothing to do other than plug into the formula. But your process is going to be, write down your formula. Area is 1/2 pi, and then fill in the missing pieces. 1/2 perimeter. Well, perimeter is going to be the side length times the number of sides. In a hexagon, it's 6. So what we have here is 6 times 6. That's perimeter. And then times the apothem, which is 5. So that gives us our area. And if we put this into our calculator, we come up with 540. All right, so that is a really basic example. You're not going to see many like this, but just to show you what ultimately we're looking to do. Let's move on to another example. In this problem, we're looking for the area of a regular pentagon with a side length of 8 and a radius of 5. So just as we did last time, let's go ahead and draw our bottom triangle and draw in our apothem, and then put in the information we're given. So we're given a side length of 8. So this side length is 8. And then the radius of the polygon is 5. Well, the radius is the distance from the center out to a vertex. So this distance is a radius, and this distance is a radius. We're going to use this right-hand side. So the radius is 5. So let's write in a 5 here. And this radius is a 5. And I'm writing both of these in just for exemplary purposes here to show you that what we have here is an isosceles triangle. Now the fact that this is an isosceles triangle is kind of important in that we know that this triangle and this triangle are congruent. and what that means to us, we'll see very, very shortly when we try to find the length of this apothem. Because in order to find the area of the regular polygon, it's 1/2 perimeter times apothem. Well, the perimeter is easy to calculate because it's just the side length times 5, which is the number of sides. So this is just 1/2 8 times 5, which is perimeter. So that's my perimeter. And then we still need that apothem. So we're still going to have to find this apothem length. Now, the fact that this is an isosceles triangle now comes into play. Because this is an isosceles triangle and the apothem is an altitude to an isosceles triangle, you'll remember that the altitude to an isosceles triangle is the perpendicular bisector of the side of that triangle. So if this whole side is 8, then that makes this piece 4. And if this is 4, we now have this leg is 4. The hypotenuse of this right triangle is 5. And we can use the Pythagorean theorem to find the apothem. So we know that a squared plus 4 squared equals 5 squared. A squared equals 5 squared minus 4 squared. And solving for a by taking the square root of both sides, the apothem equals the square root of 5 squared minus 4 squared, which is square root of 9, which is 3. Now, do you see another way we could have gotten this answer without having to go through all this work? I hope you do, because if you recall from our right triangle chapter, this is a Pythagorean triple. Now, one way you could have noticed it is notice that it's a 3, 4, 5 right triangle. The hypotenuse was 5, and one of the legs is 4. That makes the other leg 3. Again, even though this looks longer than this, never trust the picture. Only trust the information given in your picture. So this was a 3, 4, 5 right triangle, so I didn't need to even do this calculation. I could have just said, oh, it's 3 because it's a 3, 4, 5 right triangle. In either case, this is how you work it out in case you forgot. So let's take a look at what this calculation comes out to now. We have 1/2 8 times 5 times 3. Now we put that in our calculator and we're done. And that gives us 60. So that's the area of our regular polygon. Now, again, you're just going to have to use all the techniques you've developed up to this point throughout the entire course to solve these problems. There's going to be a collection of information that you're going to need to use. Let's take a look at another example. We're going to do that, though, in the next video, and so I will talk to you in the next video.